Thank you, Sophia, for inviting us for this talk. First, we started this work sometimes earlier this year, and then we submitted this paper for new reps, and it's actually accepted for the main track too. So we will be in Europe, both Charlie and me. If anyone's there in Europe, feel free to ask us more, and we can talk about these things more. So I'm in the foundations team, or now foundations team. Before, me and Charlie used to be in the same team, and we worked on this earlier this year. And Charlie's in the model efficiency team, where they do incredible stuff for inference, especially for these large language models. And this particular work stretches all the way from how we train to how we actually run inference. Yeah, so Charlie, you can take it ahead.
Yeah, thank you, Sophia, for inviting us. I'm very happy to be here and meet all the people here. So I think today we're going to share some of our work in inference, quantization, and specifically some of the very interesting properties that we found in quantizing LLMs at scale. So this is a collaboration between Cohere and Cohere for AI. Cohere for AI is the nonprofit research within Cohere. So for before we start to talk about the techniques, I want to mention something that motivates the research of quantization. So throughout the years, people have been doing research on how to improve LLMs in terms of their benchmarks, how to scale it up, and also the context lens, how we expand it. But in terms of deployment and using the LLM in production, it boils down to three things that really matters. First is the performance, second is the latency, and third is the cost to serve them. So quantization is one way we can improve the efficiency, because we all know LLMs is really expensive if we deploy them in full position as how we train the LLMs. So how quantization helps, if we look at the computes that we do in GPUs, TPUs, or CPUs, there are a few parts that takes up the memory and the time it takes to compute. First is the memory, where it holds the model parameters, and most importantly for LLMs, the activation part is the KV cache. And then for computation, there's matrix multiplication, layer norms, softmax, and all those operations. And then for data movement, it's moving the data that we store in memory to where we actually execute the kernels. So these are the main parts. And when we use quantization, we essentially, one example is to take it from 16-bit to 8-bit. Sometimes we even take it to 4-bit or lower bits. But basically, we take it from higher precision to lower precision. And so we reduce the amount for both memory, computation, and data movement. So one core thing here is NVIDIA has this int8 tensor core that provides 2 times more TOPs, which give us 2 times speed up in matrix multiplications. So if we quantize the tensors into int8, we can utilize this int8 force to speed up our computations. So you may ask, why would it work if we bring things from higher precision to lower precision? So the hypothesis is that when we are training, it requires higher precision to get the gradients correct every step when we update the parameter. But in inference time, the precision can be relaxed a bit. And then we rely on research to find a good low precision representation of the model. So when we bring it to low precision, it can still preserve the model quality. Before 2022, most of the quantization research are on vision models, mostly convolution neural networks, and encoders such as BERT. And then the there are three main techniques. One is quantization-aware training. Basically means we simulate the quantization step during training and then have the model adapt to this process of being quantized and like learn to reduce the loss with this quantization simulated. And then there's quantization aware fine-tuning, which means instead of using the full training set to adapt the model, we use a small subset. Then lastly, which is the cheapest one, is post-training quantization. So after the pre-training, we take the model and instead of doing any like backprop or change the parameter, we just compute how we quantize it after training. So before 2022, all these models are pretty small, like compared to the LLMs that we look at nowadays. So now it becomes like billion parameter size LLMs. The first two methods become less favored because they are very, very expensive. And most people start with post-training quantization. And the challenge here is like once we start to scale up and also change to LLM, which has a very different architecture compared to vision models and BERT. The previous research result may not hold anymore. So starting from 2022, people start to look into how to quantize large language models. One of the main findings of these research on quantization of large language models is that people find that there are some consistent outliers when we scale the LM to beyond 6 billion parameters. So if we quantize it to int8, it will always fail after the 6B mark. And they find that this is because of all the outliers. And then build on that observation, people start to do some strategies to make up for the outliers. For example, int8 is one kernel that actually does part of the tensor in int8 and then the outlier bit in 16-bit. So this method remedies for the outliers, which will make this curve going up again. So the accuracy will be same as like 16-bit. But the issue with this method is the kernel is a bit complicated, so it adds some overhead to the computation. So the latency is actually not improved compared to the full 16-bit inference. So this method only focus on like reducing the memory compared to FP16 instead of the latency. And there's some other work that also build on the assumption that outlier exists in the LLMs at scale and how to smooth out the outliers. But from our team, we are trying to reconcile this observation. Like, why are there consistent outliers when models scale up? Are these outliers due to nature or nurture? Or could it be relevant to the training dynamics? So this hypothesis comes from some observation from the results from previous papers. If we look at one result table from a previous work, we can see that, for example, going from 16-bit to 8-bit without much fancy techniques, OPT models drop significantly the performance, and so as the GLM models. But Bloom models are doing pretty well. In some other works, this RTN is also like when quantization is applied and full precision is the original performance. This is a precocity, so higher numbers means like worse performance. So we can see that OPT models also, the performance dropped quite a lot. But then if we look at Bloom, it is not that much degradation compared to OPT. So we can see that different models definitely have different robustness to quantization. So this gives us some hope on if we try to change the training dynamics, can we make the model more robust to quantization and avoid those fancy inference kernels so we get the latency speed up back. So comparing the different model training techniques, we chose these four axes for experimentation. First is weight decay, second is gradient clipping, third is dropout, and fourth is the data type precision, which is bflow 16 versus floating point 16. Our methodology is first we do some small experiments, which is done in a control setup. Some 6B early checkpoint. And because of the high cost of training from scratch, so we do these small experiments first to find, which, if there is any trend of like whether higher weight decay will give a more robust model. And so the same for like other axes of experiments. And then once we find a possibly more optimum choice for these training optimizations, we verify the final hypothesis on fully trained 6B, 13B, and 52B models to see if these training hyperparameters will actually give a very robust model. So some details on the models. So we use GPT-based models, which are the same architecture as as like the previous work where outliers were found. And we train a model on open source data sets from scratch. Then we evaluate the quantized models on these various downstream tasks to see their performance. So first axis, weight decay. We have these three different values of weight decay, and we try it when gradient clipping is turned off to decouple their effects. We can see there's kind of a trend of higher weight decay gives a better quantization result. So negative here means like how much the model performance dropped from FP16 to after being quantized. Second, for gradient clipping, so we tried two settings. One is with gradient clipping, one is without gradient clipping, and with all the other factors fixed in one value. We can also see that there's we can also see that with gradient clipping, we get better quantization robustness. So for dropout, the experiment suggests that with a smaller dropout, there will be a better quantization robustness. Then for data type, so there are two main data types that people use in training. One is FP16, which has a smaller dynamic range, as you can see from the chart. While bflow16 has a higher dynamic range, and it has less precision. So in training time, FP16 is a more hacky training because it requires loss scaling and sometimes you need to rewind, while FP16 is a lot more stable. So when we compare these two data types, it actually gives us the strongest signal of this may be a factor that contribute to quantization robustness. So we compared FP16 and bflow16 with different combinations of weight decay. As you can see, the purple ones here is FP16, and the green here is bflow16. And for both weight decay values, bflow16 is way more robust than FP16. And we also try this on different checkpoint steps. So there's 15K steps of training, 40K, and 75K. So in like different progress of training over time, we see consistently that B416 models are more robust.
Just a reminder to everyone, if you guys have some clarifying questions, please feel free to ask, because maybe there's lots of charts and such, maybe not everyone fully understands what's going on here. So just in case.
Yeah, for sure. Looking at the chat now. Oh, people joining. Okay. Yeah, if there's any question, feel free to interrupt. Okay. I will go on, I guess. So with these small experiments, we come up with some hypotheses on which hyperparameters will be optimal. And we tried this set of hyperparameter on a various size of models, including 355 million, 6 billion, 13 billion, and 52 billion models. We train them from scratch to like full convergence. And we see that compared to opti models, which were trained like in other training hyperparameters, our model is very, very robust to quantization. After scaling up, we don't see this degradation. Instead, these two lines of INT8 and FP16 almost align.
I see a question from Ravi. What is the y-axis on the second graph represents?
Guessing this
yeah, I assume this one, yeah.
Yeah, it's showing the y-axis here. It's also the degradation. Yeah, so like positive means the quantized model is actually slightly better than the full precision model, while the negative here means the drop. So
Thanks.
models, yeah, have significant drops here. Okay. So yeah, so this full training confirms us that the drop in model quality due to quantization can be avoided by changing the training hyperparameters, and the outlier patterns are due to nurture instead of nature. So with this technique that we makes the model more robust, we quantize the model to INT8 and receive a 40% acceleration in terms of latency and throughput. This is 1.4 times compared to FP16 inference. And then for memory, we also receive a 40%-ish reduction.
I see a question from Michael. What were hyperparameters used to train OPT FP16?
Yeah, I think the main difference is they are trained in FP16 parameters instead of B416.
Michael, do you have any follow-up questions? I mean, all the questions we can then ask after the presentation. Yeah, thanks.
Yeah, so that's of the results that we have, and the final takeaways we have is outliers are due to nurture rather than nature, and we suggest you train with B416 because it not only gives more robust quantization models, and also it's more stable training, and together with other preferred hyperparameters, you can get a model that's very robust, and then you quantize it into INT8 for 40% better efficiency and no loss in model quality.
Oh, thank you. Bharat, do you have anything to add? I don't know if maybe Bharat is not here. He had some issues. Do you guys have any questions? Please feel free to unmute yourself and ask.
Testing.
Ravi said, can you explain the testing and training data used?
Yeah. Practice. So we train with open source data, Common Crawl and C4. And evaluation data is also the common and open source one. So these are the data sets that we use for evaluation. So the tasks are pretty diverse. There are like completion tasks, co-referencing, and generation tasks. And the evaluation metric is also, we have various kinds.
I'm wondering, like, based on these findings that you guys have, like, what are sort of like next research? What are the sort of next steps after this?
I think one of the next steps is to verify this hypothesis on different architectures, see if like training with B416 will also preserve the model quality for like new architectures that comes up with like, for example, GQAs or models without bias, or models use like different position encodings. Yeah, that's one of the steps. And another thing that could be good for future work is how do we explain these patterns, right? Why would training with B416 make the model more robust? We have some analysis on the paper, but I think those are our like attempt to explain it. We don't have any theoretical explanation yet.
So currently it's only applied to LLMs, right? You don't like consider other models.
Right. Yeah, that's the focus of this work.
Ravi is asking, what is the max length input size?
Yeah, I think for answer is 22048. The adopters of our findings. Yes, I think we are one of the early adopters. So I think B416 is actually a pretty new data type for training. It's only accessible in GPUs lately, and then mostly it was accessible on TPUs. So I think whatever organizations that use TPU for training will likely observe this robustness and go for the B416 training strategy.
Yeah. I mean, TPUs are, is it on like Google or someone else is using TPUs?
Not sure who else is using TPUs, but yeah, it's provided by Google.
I see another question. Do you know if it still works with other attention mechanisms like windowed or other models? I mean, other models other than LLMs, we already kind of figure out that you guys didn't do research on this, so you don't know if it's working on other models, but other attention-based models.
Yeah, I think for this work, we keep it like the simplest attention style, just so we can compare with previous work that observed the outliers, because they don't have this window attention. But yeah, definitely in the future, it will be worth trying. Like given all the work on like expanding context lens and like trying different kinds of attention.
Regarding Eric's question about early adopters, basically, as far as you know, guys, like you are using this inside the Cohere.
Yeah. And like talking about adoption, I think one of the main feedback that we receive from audience is like we mainly experimented on training with these hyperparameters from scratch, but I think it would be easier for adoption if we verified, if we have a pre-trained model that's trained in, say, FP16, and then you can fine-tune it with BFlow16, and it will still increase the model robustness. I think that would be like applicable for wider audience. So I think that's also one of the future work that we think is worth trying.
Yeah. I see Michael is asking questions. So you guys tried like several things, gradient clipping, dropout, and such. Do you know how each of these like things that you tried impact the emergence of outliers?
Yeah. So in terms of outliers, we could only verify it in terms of like quantization loss, how much the performance dropped after being quantized. And that was our experiment results, like for higher weight decay, there's lower drop. But for outliers, unfortunately, we couldn't reproduce the outlier patterns from LLM Intake, even with the help from LLM Intake authors. So yeah, that was one of the things that we wish we really could reproduce.
I have a question from David. Did this model support? Does this model support fine tune with LoRa?
Yes. So we don't have any change in terms of like model architecture. So it's just like how in your pre-training, like how you are training it, especially changing the pre-training data type. And then after the pre-training is done with like the suggested hyperparameters, you can like add fine-tuning with LoRa or like other methods on it.
I see Ravi is asking, is quantization a better choice than pruning? I don't know. Do you want to elaborate on your question? You can just type. I understand like your mic is not working.
I think pruning, there are some work from, I think from the group that published Sparse GPT. They have some work on like using quantization and pruning together. I think Bharat have tried using pruning alone. Maybe if his mic is working, he can add to how well pruning performs.
Yeah, I see here like model pruning seems to also provide speed increases, but can both be used?
Yeah, I think there's some work on like combining them together and provide like they have a synergy and combined together there's more speed up. I think from my knowledge on pruning, like although it works on research, when it comes to deployment, it's kind of limited by the kernels provided by like NVIDIA or other companies, because if you don't have a structured sparsity, it's very hard to like deploy in inference time.
Thanks, Charlie.
I think Matthew has a question on outliers in weights or so the outliers are in activations instead of weights. This is based on so like previous works claim that there are outliers in activations. But based on our work, like if you train with the hyperparameters, there won't be any outliers in either weights or activations. So when like the previous work found that intake will like Bell SQL, they were doing like full quantization of both quantizing the weights and also the activations, so that we can use the int8 tensor cores that I mentioned earlier, like these ones. Like we want to do int8 matrix multiplications, so both the weights and activations need to be int8.
Oh, awesome. Sorry, I'm just juggling between like looking at the questions and
Yeah, me too.
sharing links. In my classic question, what do you think about training in FP8?
Yeah, I think FP8 training is very useful, but it's only present in H100 GPUs. So it's generally not very generalizable to other GPUs. Even if it and you, yeah, so I guess it's a very limiting factor. So still like int8 and int4 are more universal present in other kinds of GPUs.